this is B. Naresh, working as assistant professor in IC department. And today's topic is biasing of FET. So in this session, we are going to discuss what is the need of the biasing and how to design the biasing concepts for the field effect transistor. So actually, before going to this biasing concept, what is the need of the biasing means to identify the behavior of the any semiconductor device or either transistors like semiconductor devices like diode or transistors. So in the transistors, we have the two types. One is the bipolar junction transistor, another one is the field effect transistor. So hence, to identify the behavior or characteristics of the transistor and to design a amplify conditions, so we need to maintain a proper operating point, and there is nothing but a Q point. So for the faithful amplification point of view, means whenever we are going to design an amplifier by using the transistor, either a bipolar junction transistor or a field effect transistor, we need to define a proper operating point that is called as the Q point. And here, this operating point depends upon the external biasing between the terminals. Like if you observe the field effect transistor, we have the three types of the terminals. One is represented as source, another one is represented as a drain, another one is represented as gate. So based on the construction and the characteristics of the field effect transistor, we identify that the drain current, or in a field effect transistor, the drain current is controlled by an applied electric field between the drain to source voltage, that is represented as a VDS, and the gate to source voltage is represented as VGS. Hence, the drain current is proportional to the VDS as well as the VGS. Hence, this type of the field effect transistor is called as the field effect transistor. Why? Because of that, the drain current depends upon the applied electric field. Now, for this case, we need to maintain a proper operating point, means within the region. Suppose if you take in the bipolar junction transistor, we have the three types of the regions. One is the saturation region, one is the cutoff region, another one is the active region. For a faithful amplification point of view, we need to define the operating point in active region. That is always the center of the DC load line. Hence, to maintain a proper Q point, that is with respect to the external biasing voltage applied between the terminals. So that is the reason we require this biasing of the FET. So to maintain a proper Q point, we require the biasing, and how this external field controls the variation of the drain current. At that particular point, we need to maintain a constant drain current. So irrespective of the change in parameters like either temperature or the biasing voltage, or anything. So we need to maintain a proper drain current or a constant drain current irrespective of all these parameters to maintain a constant or a stabilized Q point. So that can be done through different mechanisms. So hence, in this session, we are going to discuss the different biasing concepts of the FET. For this case, I'm going to consider a JFET. So we have the two types of the FETs. We know that one is represented as JFET, and this is also called as junction field effect transistor. Another one is MOSFET, metal oxide semiconductor field effect transistor. So for whatever the transistor, it can be used as a amplifier. To define a proper amplification process, we need to maintain a proper Q point. Hence, we require a certain biasing concepts to maintain or to stabilize the operating point for a faithful amplification process. Hence, so we are going to discuss different biasing concepts by using this junction field effect transistor. In this case, so we have the different biasing concepts. The first one is here, it is called as the voltage divider bias. So for this case, let us consider this is a JFET, and input side we taken as a common source amplifier. So this is common source CS JFET amplifier, common source JFET amplifier. Why? Because of that, the source is the common terminal for input side and output side. So whenever the source is a common means the gate terminal. So out of these three terminals, source, drain, and a gate. So here the source is taken as a common for input side as well as output side. Hence, drain is connected at output side and the gate is connected as input side with respect to the source. And from this point of view, if you observe, the gate is biased with a VDD through the biasing components like that is R1 and R2. And from this case, and from this point, so here this circuit, this voltage from this VDD to through this biasing components R1 and R2, and this type of the network here it is called as the voltage divider network. And we need to find out how much voltage is exit with respect to the biasing voltage, that is the plus VDD. Through these biasing components, here I consider as the two resistances, that is R1 and R2. Hence, we need to find out how much biasing voltage is generates with respect to this VDD or external biasing source with respect to the biasing components R1 and R2. And for this case, then again at the output side, the drain is biased with a drain resistance. Here it is represented as RD, and the source is biased with a component that is RS. And output is taken from a drain terminal with respect to the source, and here it is also called as a drain to source voltage or the output voltage across the drain terminal. Then first we need to find out the equivalent circuit. So then I'm going to apply a Thevenin's equivalent circuit. Means, so with respect to this component, now we need to calculate how much gate voltage it generates with respect to the VDD. Means we have the two options. So directly you can use the voltage divider network or apply the Thevenin's theorem. So if you apply the voltage divider network from the circuit, we know that this VGG is equal to I into R2 from the circuit. So where we know that I is represented as, generally I is represented as, it is a ratio of voltage to the resistance, means V means VDD, and R means the total resistance. The total resistance is R1 plus R2. Hence, the VGG is represented as, so I means VDD by R1 plus R2 into this is R2. So from that point, the VGG is represented as here. So R2 by R1 plus R2 times of VDD. And this is a net voltage is affected across the gate terminal due to the biasing of VDD through the biasing resistances, that is R1 and R2. And we know that at least we required some voltage to control the drain current. And this is the required biasing voltage to allow the drain current as well as to control the drain current. Then apart from that, we need to find out how much equivalent resistance, the Thevenin's equivalent resistance, means the voltage sources are replaced with the ground. So from that, it is called as R Thevenin, or it is also called as the equivalent resistance at the gate side. So whenever this point, the input side, If these voltage sources replaced with a short circuit, means now according to this one, the R1 is the parallel combination with the R2. Hence, this R Thevenin or RG is represented as R1 R2 by R1 plus R. So according to Thevenin's equivalent, we identified the two types of the parameters. One is the voltage drop across the gate terminal with respect to the biasing voltage, as well as the equivalent resistance is generates across the gate terminal according to Thevenin's theorem. That is R Thevenin or the resistance across the gate. So from this, we need to redraw the circuit under the Thevenin's equivalent circuit. We find out this one VGG is equal to R2 by R1 plus R2 times of VD. Otherwise, you can also apply the a voltage division, means apply the KVL principle. Suppose if I taken this is a V1, so you can apply. So means from V1 to VDD node, it is represented as V1 minus VDD by across the resistance is R1. Similarly, from this V1 to ground potential, it is represented as V1 minus 0 by R2, that is equal to 0. At this point, so how we are represented means we need to find out this is V1 by R1 minus VDD by R1 plus V1 by R2 equal to 0. If I take this is V1 is a common term, means 1 by R1 plus 1 by R2, that is equal to VDD by R1. So then if you take LCM, so V1 is equal to R2 plus R1 by R1 R2, that is equal to VDD by R1. So this R1 is a get cancelled. From this, so we can write this V1 is equal to R2 by R1 plus R2 times of VD. So where this V1 I represented as that is equal to VD. So hence, so we observed from the Thevenin's equivalent circuit, the VGG is represented as R2 by R1 plus R2 times of VD. Similarly, we also observed that the Thevenin's equivalent resistance, that is RG is equal to R1 R2 by R1. That is nothing but the R1 is parallel combination with the R2. So by using these two parameters, we need to redraw the equivalent circuit, means this voltage divided by net 4 is redrawn by using the Thevenin's equivalent circuit. Means, so while drawing the Thevenin's equivalent circuit, means this input side, this should be replaced with this part is replaced with a Thevenin's equivalent voltage VGG and RG. Means at the gate side, we need to connect this voltage drop, as well as we need to connect the resistance, that is represented as that. But while determining the parameters, we need to remember this analysis. The VGG is represented as R2 by R1 plus R2 times of VDD, and RG is represented as R1 R2 by R1 plus R2. So hence, now I am going to redraw this equivalent circuit. So output side, I am not changing anything. So output side, that is a plus VDD is a plus VDD, and the drain is a biased with RD, and here also drain is a biased with RD, and the source side it is a biased with RS. But only thing we are going to modify at the input side, that input side, this part is replaced with a Thevenin's equivalent voltage, that is a VGG, and the Thevenin's equivalent resistance is RG. So this way, so you remember that the VGG means that is R2 by R1 plus R2 times of VDD. And again, you remember that RG is equal to R1 R2 by R1 plus R2, or otherwise R1 is parallel combination with R. Now we need to find out the parameters, means how much drain current. The Q point, the operating point, is depends upon the drain current as well as the output voltage. Means at output we need to define. So the output parameters are from the characteristics, already we observed that the drain characteristics in JFET as well as MOSFET. So from the characteristics, the output parameters are the drain current as well as the drain to source voltage. So these two parameters defines the to stabilizing the Q point or to maintain the proper Q point, means how much drain current is required and how much drain to source voltage is required to produce the a faithful amplification by using the field effect transistor. So hence, now I'm going to calculate. So just can apply the KVL at input side. So that you can take this loop. So here I represented this VGG is replaced with VG, means the voltage across the gate side. So means this is a source to this input side, VG is equal to, and let us assume that which current is the flows. This RG is connected across the gate terminal, hence it allows the gate current. And in between this gate and the source, a potential difference is there, that is represented as VGS, as well as the voltage drop across the source resistance is represented as Vs. Hence, Vg is equal to the voltage means, so this is voltage drop across this Rg is represented as V is equal, generally we know that V is equal to I into R. I means which current is the flows? Ig, hence Ig times of Rg plus the potential difference between gate and a source, that is represented as Vgs, and the voltage drop across the Rs. So we can directly write Vs, or you can also write Is into Rs. So hence simply first I represent Vs. Now I'm going to replace this Vs with Is into Rs. So hence Vg is equal to Ig times of Rg plus Vgs is the Vgs plus the voltage source. From this circuit we know that Vs is equal to Is into Rs. And generally, again, if you recall the BJT operation, we know that the emitter current is a summation of base current and collector current. So based on that, in FET also, the emitter is simply replaced with the source. Hence, the source current is a combination with the gate current as well as the drain current. Or otherwise, Is is approximately equal to drain current. So why? Because of the gate current is a very small, that is negligible. So that is the reason we taken as the source current is approximately equal to drain. And here I represented with this Is is the summation of drain current as well as the gate current. Hence I represented as Id plus Id times of Rs. And from this JFET, so if you observe the JFET analysis, and we know that the gate current is very small. Why? Because the gate is biased with reverse voltage. Hence, let us consider that if Ig is a 0, means if Ig is a 0, what happens? This term is a replaced 0 times of Rg, and here this is, so Ig is again 0, means it is 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 approximately equal to Id. What we observe like this, Is is approximately equal to Id. Hence, the Vg becomes only the Vgs term plus in this, so Id plus 0 times of Rs. Hence, that becomes Id times of Rs. So this is a gate voltage is required to bias the gate terminal. And from this, I am going to calculate the VGS. VGS is equal to, from this, Vg minus Id times of Rs. Okay. So from the characteristics, either the drain characteristics or the transfer characteristics, Id, the drain current is a functioning of, with respect to the biasing voltage is applied between drain and the source as well as the gate and the source. So these two parameters to control the flow of drain current. Hence, if you want to stabilize this drain current, we need to maintain a proper biasing voltages between the gate to source as well as the drain to source. Hence, we observe from this biasing parameter from this voltage divided bias concept, we observed how much gate to source voltage is required, that is represented as VGS is equal to VG minus ID into RS, where we know that the VG is represented as, from the according to Thevenin's theorem, equivalent VG or VGG, that is equal to R2 by R1 plus R2 times of VDD. So this is the Thevenin's equivalent voltage due to the biasing concept. Now we need to calculate. Now again from the output loop, now we need to calculate. So the input, from the input side, we observe this VGS parameter. And again, if you want to write the potential difference between drain and the source, it is represented as the VDS. And here the voltage drop is represented as the VS. And at this point, the current is flowed as a drain current. Now, if you consider the output loop, we need to take from the plus VDD to the lower potential here. So we need to take from the plus VDD to the lower potential, or is nothing but a ground. So from this, you have to write, for this case, apply the KVL. So VDD means this is the source. VDD is equal to the voltage drop across this resistance, that is VD, is equal to ID into RD, along with the voltage drop between the drain and the source is represented as the VDS, along with the voltage drop across the source resistance is represented as VS. So now I'm going to write these three parameters. Hence, so VDD is equal to ID times of RD plus VDS plus VS. Or otherwise, this ID RD, you can also write this VD, means VDD is equal to ID RD is represented by VD, and the potential difference in terms of voltage I'm writing. The potential difference between drain and source is represented as the VDS, and the voltage drop across the source resistance is represented as VS. So from the circuit, from this equivalent circuit, we know this VD is equal to, means the voltage drop across the drain resistance is represented as ID times of capital RD. And similarly, the voltage drop across the source resistance VS, that is represented as IS times of RS. So hence, I replace it with this VD is replaced with ID times of RD, and the VDS is the VDS, and the VS is the VS. Now, and this VS is represented as IS times of RS. And further simplification, and we know that from the again this characteristics, so we observe that what we observed, the IS is represented as the summation of gate current as well as the drain current. So at this point, when under this point of representation, we know that the gate current is a very small. Hence, we assume that IG is equal to 0. If IG is equal to 0, the source current is approximately equal to your drain current. Hence, IS is also be taken as the drain current. Hence, I am going to represent. So, hence the same point I represented, since we assume that the gate current is a very small, hence it is a negligible. Hence, I consider this IG is a 0. Then we assume that the drain current is or the source current is approximately equal to ID. Now I can substitute this IS with ID. So what happens now? This VDD is equal to VDD. They substituted that. Means either you can substitute either IS is equal to ID, means you can substitute ID with IS, or IS with ID. Hence, I substituted this one. So ID is replaced with IS, RD is RD, VDS is a VDS, and IS into RS. So from these two terminals, this is the first term and this is the third term. From this 1 and 3, IS is a common. If you have taken the IS is a common, it is represented as RD plus RS plus VDS. So now, which one we need to define? So that is a reason. So if you recall this one, the field effect transistor definition. The drain current is a control with the functioning of VDS as well as the VGS. That is the reason. So in the from the input loop operation, from the input loop, we observe that how much biasing voltage is required between the gate and the source to maintain a proper drain current. Similarly, we need to find out how much biasing voltage is required across the drain and the source to maintain the proper drain current or to maintain a proper operating point or to fixing the Q point for the faithful amplification pointer. So that is the reason. Already we observed this VGS parameter. Now we need to determine how much biasing voltage is required between the drain and the source. Hence, from this relation, I need to determine this VDS. So hence, VDS is equal to VDD minus this is IS times of RD plus RS. So from this Thevenin sequence circuit or this from this voltage divided by a circuit, we identified these two parameters, VGS parameter as well as the VDS parameter. So if you observe this VGS, so the VGS is represented as VG minus ID times of RS. Or otherwise, you can also write this is VGS is equal to VG minus. You can also write IS into RS. And another one, we observe that the VDS parameter, that is VDS parameter is VDD minus IS into RD plus RS. Or otherwise, you can also write this is VDS is equal to VDD minus ID times of why because IS is also approximately equal to drain current. So hence, you can also write this VDS is equal to VDD minus ID times of RD plus RS. So now, so from this voltage divided by us, we identified that so how the drain current is maintained a constant or how we are maintaining the Q point, a proper Q point by the applying of either the VGS or a VDS. So if any temperature is changes, and we know that if for every 10 degrees centigrade, the reverse saturation current becomes double. So that is the reason. From the temperature effect parameters, for every 10 degrees centigrade, it becomes or it doubles the reverse saturation current. Hence, it also affects the major current, that is drain current. So if the drain current is changes, if you observe the previous voltage divided network, let us consider if ID is a changes here, if ID is a changes, so what we observe, the source current is approximately equal to ID. So hence, so at this point, if ID is a changes, IS is also changes. So IS is a changes means again means there is no proper maintaining of a operating point. Means this is drain current is the changes. So here due to the temperature, so the Q point is not becoming constant. To irrespective of this all these parameter, even though if the temperature is changes, we need to maintain a proper or a constant drain current. So now we need to adjust internally. So how much drain current is the changes, that should be compensated through our biasing components. For this case, we are going to use another biasing concept, that is self bias. So why it is called the self bias means, let us consider if ID is a changes and we know that IS is also changes. And from this, let us take according to this circuit configuration, and we know that the VGS is represented as, so what is the pronouncing observation? VGS means the potential difference between gate and the source, means we can write like this. VGS is also represented as the potential difference between gate voltage and the source voltage. And here, let us consider the gate voltage is a 0, means 0 minus Vs. We observe that VGS is equal to minus Vs, means, so that VGS is equal to minus Vs means that is equal to minus Is into Rs. Let us consider if temperature is changes, the reverse saturation current is changes. If a reverse saturation current is changes, the major current means drain current is also affected. If this drain current is affected, so that IS is approximately equal to drain current, hence IS is also affected. If IS is affected, the Q point is also affected. So hence, to maintain a proper Q point, so now we are going to use the cell bias concept. Under this case, what happens? If IS is changes means this voltage drop VS is also changes. If a VS is the change is more negative, if a VS is the change is more negative, so previously if take as some voltage, due to this increasing of the temperature and due to this increasing of the drain current, then it also affects on the source current. And due to this increase of source current, the voltage drop across this RS is also changes. If the voltage drop across this RS is changes, so that will be effects on the input parameter. Means this affects the VGG parameter. Means this VGG is becomes more negative. So if a VGG becomes more negative, whenever the drain current changes, or whenever the voltage drop across the source resistance changes, that changes the more negative voltage across the gate. So means that, and from the drain characteristics, we observe that for a JFET, so when VGS is equal to 0, it observes the drain current. This is the VGS is equal to 0. When a VGS is a decrease from the 0, drain current is a decrease. Means this is VGS is equal suppose minus 1 volt. And this is when VGS is equal some minus 2 volts. So at large reverse voltage, we observe that the drain current is 0. So hence, if a VGS is further reduces, the drain current is also reduces. Hence, to compensate this drain current, so that can be done through this self-biasing concept. So hence, when the voltage drop across the source resistance is the changes, that affects the or to reduce the gate voltage. Whenever the gate voltage is reduced from the 0, it reduces the drain current. Means how much drain current is increases, that amount of drain current is reduced by the compensating of this gate to source voltage or the voltage drop across the gate. Hence, this type of the compensation or this type of the biasing is called as the self-biasing for the FET to maintain a proper Q point. So for this case, here to design this self-bias, so here we removed from this a voltage divided network from the VDD, and we assume that the gate voltage is 0. And just simply we taken as this internal input resistance, that is RG. So means we need to offer a maximum, a large resistance. Why? Because of that, we assume that the gate current is a 0. So if you want to maintain a minimum gate current, the gate resistance should be infinite. So hence, where this RG should be the large gate resistance, it offers a minimum gate current. Then, and the drain is a biased with a external resistance, that is represented as RD, and the source terminal is a biased with external resistance, that is RS. The voltage drop across the source resistance is Vs, and the current flowing from the drain is represented as ID. Now we need to calculate the parameters. So what are the parameters are required to maintain a proper Q point? So just now we discovered that. So the parameters are VGS as well as the VDS. So these are the two biasing voltages are required to maintain a proper Q point or to maintain a proper drain current. So hence, so from this, I use that. So if I take in this one, so when the output side, if you consider this output side, so how to write this output side loop? So means VDD is equal to the voltage drop across this RD is represented as I, means otherwise I'm writing this VD plus, and this is another one is a VDS, and the voltage drop is across the source is Vs. Hence this VDD is equal to VD means ID into RD plus and VDS, and this is IS into RS. So hence, so from this we know that VDS is equal to VDD minus IDRD minus IS into RS. So that is the reason here represented as this is VDS is equal to VDD minus ID into RD minus IS into RS. And generally we know that IS is equal to IG plus ID. When if we assume that IG is equal to 0, why would that? The gate current is a very small, hence IS is approximately equal to ID. So when under this condition, this VDS becomes VDD minus ID times of RD minus ID times of RS. Hence the same point here I represented. So that is VDS is equal to VDD minus ID times of RD minus ID times of RS. From these two terms, if you take an ID is a common, hence VDS is equal to VDD minus ID into RD plus RS. Now again we need to calculate. So up to this point, so we calculated that the drain current is a functioning of VDS. Means while applying the KVL at the output side, we identified that how much drain to source biasing voltage is required to maintain a proper Q point, or required the proper drain current to allow the faithful amplification by using the field effect transistor. Now we need to calculate how much a gate to source voltage is required to limit the flow of drain current. So hence we need to apply a KVL at the input side. So from this we know that from the gate to source voltage. See here we taken as the VGG is a 0, hence. So how to write this one here, this VGG. So means if you are writing like this, VGG is equal to, so this is the source, we assume VGG is a 0, and that is equal to the potential difference between gate and the source is represented as VGS, along with the voltage drop across this RS resistance is represented as VS. So this is a loop equation from the input side, that is equal to VGG is equal to VGS plus VS. And now what we need to calculate, so we need to determine the VGS, how much biasing voltage is required between the gate and the source. So hence from this I need to determine the VGS is equal to VGG minus VS. And from this self-bias concept, we assume that the gate voltage is represented as 0. Why? Because of the for N-channel JFET, the gate is always reverse bias to limit the flow of drain current from the drain to source. Hence, the most practically we assume that the gate current is very small. Hence, so we taken as the VGG is also 0 here. So hence VGS is equal to 0 minus VS. Hence that is nothing but a VGS is equal to minus VS. This is from the loop. Or if you take in the potential difference between this and VGS, so again that way, so this is represented as the potential difference between gate voltage and the source voltage. From this self-bias circuit, so what we take in for this self-bias circuit, when the temperature changes, so then it also affects the drain current. To compensate this drain current, that can be compensated through the variation of this voltage drop across the source to limit or to reduce the change in drain current with respect to the temperature. Hence, and we assume that, so how much gate voltage we applied here? So VG is a 0 and 0 minus VS. Hence, this VGS is also represented as minus VS. And this voltage, so whenever the drain current changes, it also changes the VS voltage. That the voltage drop is changes towards the negative direction. Hence, whenever the gate voltage is changes towards the negative direction, it limits the flow of drain current or it reduces the flow of drain current. So hence, automatically the circuit itself it compensates the change in drain current with respect to the change in temperature. So hence, from these two observations, so we calculated as the VGS as well as the VDS. What we observed, VDS is equal to VDD minus ID times of RD plus RS, and the VGS we observed that is minus VS. So these are the two biasing voltages are required to maintain a proper Q point for the field effect transistor. So up to this point, today we observed that what is the importance of the biasing and what are the types of the biasings are required to maintain a proper Q point by using the field effect transistor. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.